You are given a parallel plate capacitor structure of plate spacing D1 plus D2 and plate area S. In the region from 0 to D1 is a material with permittivity of epsilon sub 1, and from D1 to D1 plus D2, a material with permittivity epsilon sub 2. You are to find the capacitance of this structure, but you are not to use circuit concepts. If you use circuit concepts, you would get no credit for a problem like this on an exam. You should assume you know nothing about circuits when you treat these problems. Approach them from a fundamental concepts point of view. This way, you will develop a greater understanding and mental model for the charges involved, the resulting fields, and the capacitance of this structure. When we apply a voltage across the capacitor, charge will develop on the plates. That is free charge, and the only place in this structure we will have free charge. Electric flux density begins on positive free charge and terminates on negative free charge. So the electric flux density field will be the same in both materials. Let's look in a little more detail about what's going on inside this capacitor structure. For illustrative purposes, I opened up gaps between the two dielectrics and between the plates and the dielectrics. Since the materials have different dielectric constants, they will polarize differently. So let's assume the permittivity of material 2 is greater than the permittivity of material 1. So you'll get more bound charge forming in material 2 than material 1. So this surface here has a greater density of bound charge than this surface right here. The lines we're seeing are indicating electric field intensity. So electric field intensity begins on positive free charge or positive bound charge, and it terminates on negative free charge or negative bound charge. The electric flux density fields have to be the same in the two dielectrics because the electric flux density field is beginning on the positive free charge on the left plate and terminating on the negative free charge on the right plate. So that electric flux density field is equal to the charge density on our plate, which is the total charge on our plate divided by the plate area S. We obtain the electric field intensity by dividing the electric flux density by the permittivity of the material. Since the electric flux density field is rho sub S in the x direction in both materials, we obtain the electric field intensities by dividing by the permittivities in the two materials. So the electric field intensities will be different in the two materials. Now that we have the electric field intensities in the two materials, we can find the potential drop based on these two electric field intensities. So minus the integral of E2 from D1 plus D2 to D1 minus the integral from D1 to 0 of E1 dx will give us the voltage drop across our capacitor. We'll substitute rho sub S over epsilon sub 1 for E sub 1 and rho sub S over epsilon sub 2 for E sub 2. Performing these two integrations, we get this expression for our voltage across our capacitor. Rho sub S is just the total charge on the capacitor divided by the area of the capacitor plates. So we'll make that substitution for rho sub S. And we can just rearrange this equation to get Q over V, which will be the capacitance of our structure. Which I've rewritten here. This expression is the capacitance of a parallel plate capacitor of plate area S, a material of permittivity epsilon sub 1 between the plates, and a plate spacing of D1. Similarly, this is an expression of the capacitance of a parallel plate capacitor of plate area S, a material with permittivity epsilon sub 2 between the plates, and a plate spacing of D2. So this term is 1 over C sub 2, and this term is 1 over C sub 1. So the capacitance of this structure is the same as that of two capacitors in series, where one of the capacitors would be associated with this region right here, that's C sub 1, and the other capacitor would be associated with this region right here, that's C sub 2. Using circuit concepts, you could quickly obtain the capacitance for this structure without really understanding the fundamental concepts of the charges involved and the resulting fields. That is why you must approach these problems from a fundamental concept, so you will develop those insights and mental models.